Okay, so I have to admit something to y'all, which is that I am not a professor yet, and I have not really taught a class before, so you're my guinea pigs. I was going to do this on a blackboard, and I was told maybe that's not a good idea, which is very appropriate because there is no blackboard. Also because they're supposed to record this for posterity. So I wrote all of these equations that you're about to see in PowerPoint. So please do give me feedback as to the pacing of this. If I'm going too fast, please let me know. If it's illegible, please let me know. And if this is just mind-numbingly too mathy, I apologize. And please give me some feedback because
everyone will have the slides. So
okay.
This is maybe appropriate to go back and look at things later.
Okay.
If you're here for a few days. So.
Right. So in the winter quarter, I'm going to be teaching a class, a graduate seminar on chemical evolution. So if you have any feedback for how I can improve my teaching ability, please do let me know, because you're the perfect guinea pigs for this. And I apologize that you have to be the guinea pigs and not the final subjects. So this lecture will be all based on this book, Chapter 7 and 8 of this book. This is an excellent book. It's Bernard Pagel's Nucleosynthesis and Chemical Evolution of Galaxies. There's another great book which I have been meaning to buy for a while. It's Francesca Mattiucci's book, Matteucci. She also wrote a very excellent book on galactic chemical evolution. I've been meaning to buy it and read it and maybe use it as a basis for my class. So this lecture we're going to be learning about the equations of galactic chemical evolution, and then we're going to make some analytic solutions to those equations. So in the workshop today, we're going to be doing numerical solutions to those equations. We're going to have to worry about doing the integrals ourselves. But today, we're going to be doing analytic solution to these equations. So some of this is going to be a little bit hokey. We're going to be assuming things just for the convenience of finding analytic solutions to the equations, but they're still going to be educational. They may not be that grounded in reality, but they're going to be educational. And so the specific chemical evolution models that we're going to be considering are the closed box model, which means that nothing gets in, nothing goes out. And also a leaky box model, which is that nothing gets in, but things can get out. And also an inflow model, where all bets are off and things can come in and things can go out. So here are some very helpful references. Beatrice Tinsley basically codified this field of galactic chemical evolution in this really awesome article, Fundamentals of Cosmic Physics in 1980. Unfortunately, this thing is very difficult to find online, but it basically is the origin of this field. And Beatrice Tinsley was actually a really amazing person. She found out in 1978 that she had an incurable cancer. And what she wanted to do before she died was to make sure that she gave the astronomy community all of the knowledge that she had gathered over the last few years of her life. And so she worked very hard to make this article in 1980, and the next year she died. So it was a very excellent gift that she gave to the astronomical community before she passed away. Andy McWilliam wrote this review on chemical evolution of the galaxy in 1997. That's a very good one. As you can tell, it's probably a little bit out of date. So Francesca's book, I also mentioned, is also a very good one. And also, a lot of the workshop today is going to be based on my own paper from 3 years ago, the alpha element distributions in Milky Way satellite galaxies. So in that paper, I go through a lot of gory detail about how I constructed my chemical evolution model, probably more than anyone who ever read AppJ actually read in the article. But if you're interested, and if you need any hints today on the workshop, it might be useful to have a look at section 2 of that paper. Okay, so one of the basic things you need for these chemical evolution models. I should also apologize. I didn't have quite time to review all of these equations, so I hope everything goes smoothly. I was intending to do this tomorrow, but we'll wing it. So one of the things you need to know before you blow up stars is which stars to blow up. So the initial mass function tells you how many stars are in a galaxy and what masses are those stars. So how many, in particular for our chemical evolution model, what we want to know is how many stars in the galaxy are massive enough to blow up as type 2 supernova, and how many stars are low mass enough to blow up as type 1a supernova. So the initial mass function, as you know, tells you the number distribution of stars as a function of mass. And when I have these brackets like this, that means that's the units of the variable that we're considering. So the units of phi are per solar mass. We're going to normalize phi such that the integral from some lower mass limit to the upper mass limit of m phi, which is the total mass of stars in the system, is 1. So the total, we'll just say that phi is normalized such that the entire mass of stars in the system is one solar mass. It's a particularly low normalization. Obviously, you're not going to get a whole population of stars that has only one solar mass. But just for convenience, we're going to assume that phi is normalized to 1. Or more specifically, m phi is normalized to 1. So we're going to also assume that the lower mass limit of stars is 0.08 solar masses. That's just because that's what I had in my graduate classes, so why not? And the upper mass limit is going to be 100 solar masses, same reason. The saltpeter IMF has a power law of m to the negative 2.35, and in this normalization, I've already done the integral for you, it's 0.17. There's also some more sophisticated IMFs, like the Krupa 2001 IMF, which breaks it up into different bins of stellar mass. So for the very high mass stars, you get a different power law slope than the low mass stars. And in particular, for the lower mass stars, you get a shallower and shallower slope. I did all this integrals on a piece of paper. I hope I got my numbers right. But if you integrate this thing m phi, then hopefully you do, in fact, get 1 when you add all those things up together. OK, so stellar lifetimes I already brought up in the previous lecture. It varies slightly with the metallicity of the star. So if we have a solar metallicity star, this is just an empirical formula for what the lifetime of a star is. I just fit this equation to the empirically measured lifetimes of stars as a function of initial stellar mass. Remember, this is initial stellar mass, not the star that ends, not the mass that the star ends its life with, but the mass that the star started its life. And if you go down to about a 20th solar, it's a slightly different, it's not that much different, but it's slightly different lifetime for the star. In my 2011 paper, I assumed that all stars had the same lifetime regardless of metallicity, and that's a very good assumption. OK. That's preliminary stuff. We have the IMF, we have the lifetimes of stars. Now we're going to go into the basic equations of galactic chemical evolution. So this is beginning chapter 7 of Pagel's textbook. So we're just going to define a bunch of stuff. So we have the entire mass of the galaxy is equal to the mass in gas plus the mass in stars. So this is a very complex concept, I know, to add together two things to get another thing. So we have the entire galaxy mass, and we have the mass in gas and stars. Of course, the units are going to be solar masses. The change in the mass as a function of time is equal to the stuff falling into the galaxy, that's F, to the stuff ejected from the galaxy, E. So if the entire galaxy mass is changing as a function of time, it's because something's coming in or something's going out. So implicit in these two equations is the fact that we're dealing with the galaxy as just a one-zone thing. It's just one little zone. So you can imagine it like a permeable balloon. Inside the permeable balloon, we have a mass m. And then if stuff goes out of it, then we have this E, negative E. We're losing mass from the galaxy. If stuff goes into it, we have this F. So basically, we're counting everything inside of this permeable balloon as part of the galaxy. Everything outside of it is beyond the scope of what we're dealing with. OK, so we have the infall into the galaxy, and we have the ejection in a galactic wind. And so usually, when we talk about ejection in a galactic wind, it's usually because of supernova feedback. When a supernova blows up, it injects a lot of energy into the surrounding interstellar medium, enough so that some of it can be unbound from the galaxy. Now we can break up this dm/dt into the change not just in the total mass of the galaxy, but the change in the gas mass. So the change in the gas mass is equal to gas falling into the galaxy, so that is a positive increase in the gas mass. Gas loss, presumably due to supernova feedback. And we also have these two other variables here. One is stellar ejecta, so we reclaim stuff from stars. So when stars blow up, they return some of the stuff they borrowed from the gas. And in this case, it's going to be altered in its chemical composition, which we'll deal with later. But for right now, we're just dealing with the total mass. We don't care right now what the gas is made of. We're just dealing with the total mass. And then gas is also lost due to the star formation rate. So whenever we form a star, we have to borrow from the gas in the galaxy to make that star. Now, the change in the stellar mass is just the last two of these variables. So when we form stars, we increase the stellar mass, of course. And when the stars blow up and they return some ejecta, then the stellar mass decreases. Now, this stellar ejecta thing is given by this equation. We have the mass of the stars minus the mass in the remnants. So when the star dies, it leaves behind a remnant. And so the difference between the mass of the star and the mass of what it leaves behind is what it returns to the interstellar medium. Does that make sense? So we have a star that starts off with mass m. It leaves behind a remnant of mass m rem. So the difference is whatever it returns to the galaxy. So if we integrate this quantity times the star formation rate times the initial mass function, then we get all of the mass returned from stars that are dying. We have to integrate that from the mass of a star at time t. So remember, the lifetime of a star increases as the stellar mass decreases. So at a certain time in the galaxy, that corresponds to a certain mass of star that's dying at that particular time in the galaxy. So if we wait a certain amount of time, then we have a high mass star dying, and we wait a longer time, then we have a low mass star dying. So this lower limit of integration depends on how long we wait. And the upper limit of integration is always going to be 100 solar masses, just because we assumed it that way. And if we integrate this from m tau to mu, then we get all of the mass returned from stellar ejecta. Now we can write all together the change in the gas mass times the metallicity. So the metallicity is just the fraction of the gas mass in heavy metals. So Z is just the mass in heavy metals divided by the total mass. And that change is equal to the ejecta, now with subscript Z, and I'll write down here what E subscript Z is, minus Z times the star formation rate. So we're losing metals from the gas into stars. So when a star is formed, it adopts the metallicity of the interstellar medium. So when we form stars according to phi, then those stars formed with metallicity Z. It just adopts the metallicity of the ISM. We lose metals according to this part of this term in the equation, and the loss of metals does not necessarily have to be the same as the interstellar medium. If the ejecta is not well mixed with the rest of the galaxy, oh, sorry, this is the loss term, ZE. If the ejecta is not well mixed with the interstellar medium, then we can actually lose metals at a different metallicity than the rest of the galaxy. So for example, if we have a supernova blowing up, and that supernova ejecta just directly gets expelled into outer space, then the metallicity of that ejecta is much higher than the surrounding interstellar medium. So we're allowing for the metallicity of the ejecta to be different from the ISM. Similarly, we're allowing for the metallicity of infalling gas to be different from the ISM. And that makes a lot of sense, because if gas is falling into the galaxy, it doesn't have any idea what the metallicity of that galaxy is. And we usually tend to assume that ZF is 0. We usually tend to assume that the metallicity of gas falling into the galaxy is 0. So that, in other words, it's pure hydrogen gas falling into the galaxy. So this is, Z, remember, is the mass of an element, particularly a metal, the mass of a metal divided by the total mass. And then this EZ is the stellar ejecta in metal C. And the units are solar masses per year for both of these things. And here's the equation for EZ. It's one of the more complicated equations that you're going to see, but it's not that complicated, so we'll walk through it. So this term here is very similar to this term here. The only difference is now we have this Z term here and this MQZ term. So this Z term is just saying what is the metallicity at the time the star was formed. So Z of t is the metallicity of the interstellar medium now. Z of t minus tau is what was the metallicity of the interstellar medium at the time the star was formed. Because the stars adopt the metallicity of the ISM at the time they were formed. But stars also make elements as well. And so this MQZ term accounts for the fact that stars are in fact making elements when they blow up. So QZ is the yield of the element Z. So when the star blows up, it generates from nothing in this model a new mass of element Z, and it returns that to the interstellar medium. OK, so I'm about to go to the next slide. So if anyone has any questions, just let me know. Yes, please.
So Q is the fraction of the total ejected mass there, is that correct?
Yes, it is the ejecta in metals as a function of the initial mass of the star. Is that what you said? I think that's what you said.
The fraction was the key word that I wanted.
That's correct, yes. So QZ, we take a star of initial mass m. QZ is the fraction of that initial mass, not the star that the mass blows up with, but the initial mass of the star that's generated in element Z. Make sense? OK, so now I'm going to go to the next slide. OK? OK, so now I'm going to define this variable r, which is called the return fraction. So basically, how much how much mass in stars gets returned for a given amount of mass in stars formed. So it's just the difference between the mass in the star and the mass of the remnant of the star multiplied by the initial mass function. So all this is if we formed x solar masses of stars, then x times r solar masses of stars gets returned to the interstellar medium. We're also going to define alpha to be 1 minus r, just for convenience. So this return fraction. The units are unitless. So we have nothing in these brackets. Okay. So this is an empirical formula for the mass of the remnant. It does not apply to all ranges of stellar masses, but it's pretty good for massive stars. And so the mass of the remnant just obeys this linear equation. As you can see, it does not work for very low mass stars because let's say we have a 0.1 solar mass star. The mass of the remnant would in fact be more than 0.1 solar masses. So you cannot extend this down to very, very low stellar masses. It only works for basically the range of core collapse supernova. Now we're going to define something called the yield, or more specifically, the effective yield of the system. The effective yield of the system is equal to alpha to the negative 1 times this integral here. And so it's the mass of the star times the yield. Remember, it's the fractional yield of what's being made in element I times the initial mass function. So what this effective yield means is for a given mass of stars formed, how much out of all of those stars gets returned to the interstellar medium in element I. And so now this incorporates the return fraction into it as well. So the previous this Q thing is just for one particular star. Integrating over the entire initial mass function gives you all of the elements from all of the stars formed being returned to the interstellar medium. So that's what P is.
This assumes that what the star's remnant is the same metallicity as what's ejected.
This assumes that the star's What did we assume?
It assumes that what produced in the core is ejected at the same fraction as hydrogen. Or does it not?
So where are we assuming what the metallicity of the core is, of the remnant is?
Because, I mean, you're just saying you take the return rate and you apply that to whatever is produced in the star. Could be produced in the core and then never gets out of the star.
That's correct, but so Q here is defined to be what gets out of the star. So we're just going to define Q to be what gets out of the star. So whatever is ended up in the core is not part of Q. Okay. And so remember again that Qi is the fraction of the initial stellar mass in element I that's generated and gets out of the star. We'll just define it to be that way. Is that good? Does that alleviate that concern? Okay. And the units of P are solar masses. Okay, so now these are very complicated equations, and we can solve them not that complicatedly in a computer, but we want analytical solutions so we can actually draw lines on plots with analytical approximations to everything. And so the most important analytical approximation that we can make is the instantaneous recycling approximation. Instantaneous recycling means as soon as we make it, it blows up. So as soon as a star is formed, it blows up and it spews its ejecta into the interstellar medium instantaneously. So analytically, this is what the instantaneous recycling approximation looks like. Numerically, what that means is in the same time step, as soon as the star is formed, it blows up. So now we're going to define a variable S of T, which is just the total mass in stars ever to have formed, regardless of whether or not those stars have blown up. The total mass in stars ever to have formed is just the integral of the star formation rate from 0 to now. The total mass in stars now also accounts for the return fraction. So we take the total mass of stars ever to have formed and we multiply by 1 minus the return fraction to get the total mass in stars still existing today. Does that make sense? Because some of those stars are going to be blowing up and returning gas to the interstellar medium, which decreases the stellar mass and raises the gas mass. So the total mass in stars now is the total mass in stars ever to have formed multiplied by 1 minus the return fraction. Okay, so that's all stars born by time t, not accounting for mass loss. And then a little s also accounts for mass loss now. That's what alpha does. So now with the instantaneous recycling approximation, we can simplify the equation for g. So dg dt is now just the mass flowing in onto the galaxy, the mass flowing out of the galaxy, and then we lose gas due to star formation as well. Okay, so now we can multiply through by dg ds, because we know what ds dt is. ds dt is just alpha phi. So ds dt is alpha d capital S dt, and d capital S dt is just phi. So if we have dg dt is this, then dg ds is just this. You might be wondering, why am I doing this? And a lot of the things that we're going to be doing is just manipulating the equations until eventually it looks like it's all confusing, but all of a sudden something magical happens, and we can write this equation that explains the metallicity distribution of stars. And so I can do this by virtue of knowing that d little s dt is alpha d capital S dt, which is alpha phi. Everybody follow so far? So what I did to go from here to here is just divide by ds dt. Okay. So now we have this really complicated equation. Remember, this is from 2 slides ago. And we can simplify it quite a bit from the instantaneous recycling approximation. The instantaneous recycling approximation is equivalent to saying that the lifetime of a star is 0. So as soon as a star is formed, it blows up. So instead of having the metallicity of t now minus the lifetime of a star, we can just have the metallicity of now. Because as soon as a star blows up, as soon as a star forms now, it blows up now. And the same thing here. We don't have to worry about what the star formation was like tau million years ago. All we have to do is worry about what the star formation rate is like now. And so this equation simplifies quite a lot. It simplifies to this. I just got rid of the taus. And so this simplifies quite drastically to just this. So this is the definition for r. M minus m rem times phi psi is just the definition for r. And then we have a z multiplied in there. See, the time dependence is not part of this integral, so I can just pull it out of the integral. The only part of the dependence of the integral that we had to worry about before was the dependence on the mass. But the tau dependence on mass has just gone away, so we can really simplify this integral quite a lot. And then this other thing here, mq phi psi is just alpha times p, is psi times alpha times p. So we can simplify this equation quite drastically. So now we can take the equation that we have from slide 5. I'm just rewriting the equation from slide 5. We can rewrite Ez as phi times Rz plus alpha p, and that's what I've done here. So Ez is now alpha p plus Rz. And I've also divided through by d capital S dt. So when I divide through by d capital S dt, that's just dividing through by phi. Remember from the previous slide, oops, I just made a screenshot. From the previous slide, we know that d capital S dt is just d capital S dt is just phi. Okay? So if I divide this equation through by d capital S dt, then I'm dividing through by phi, which is why all of a sudden I have these phi's in the denominator here. Remember, this is the star formation rate. I keep saying phi, but it's actually psi. Okay, now let's assume also that we have a homogeneous wind. So the stuff coming out of the galaxy we're going to assume is instantaneously mixed. So this is the same thing as saying this is an instantaneous mixing approximation. So now we've made 2 approximations. Instantaneous recycling, where the lifetime of a star is 0, and now instantaneous mixing, where as soon as the stuff gets blown out into the interstellar medium, it's all instantaneously mixed. And that's also implicit in this one-zone model. If we only have one zone in the galaxy, we can't really deal with different parts of the galaxy having different metallicity. So as soon as the stuff gets blown out, it's well mixed into the entire ISM. So that also implies that when we lose stuff from the galaxy, the metallicity of stuff being lost from the galaxy is the same thing as the metallicity of the ISM. So that's going to simplify this equation quite a lot. So now we have d little s now. So going from big S to little s just means dividing by alpha. And we have this alpha p turns into p. I've taken this z out here, so I have minus z. There's that 1. Here's that e over alpha phi. And here's this zf times f over alpha psi. Alpha psi. Alpha psi. Okay.
So we're missing the factor of 1 over alpha.
Where?
You have minus c. You didn't divide the minus c by alpha.
No, because this is 1 minus r, which is the definition of alpha.
Oh.
Make sense? Okay. Okay, I'll just pause for a bit. Everybody catch up. Is that all good? So again, this is all just going to be a big mess of equations until it all magically comes together. So we're just manipulating equations until something magical happens. Okay, so now I'm going to move this thing around to the top there. Okay, so it's the same equation. And now I can say that's just equal to z dg ds plus g dz ds. And then we know that from the equations on previous slides tell us that this is just the definition of dg ds, and this is just the equation of dz ds. Okay. We know that because dg ds is equal to f minus e divided by alpha psi minus 1. That's from slide 7. Okay? Does everybody follow that? This is just a bunch of algebra. You can trust me. And now I can manipulate this around. So what I did to go from here to here was just do the chain rule. So dg ds times z, dz ds times g. And so now I can say, just move things around here. So I take this right side of the equation here, I take this left side of the equation here, things get moved around. Okay, so I'm just going to save these two equations for a bit. I'm going to go introduce something new, and then I'm going to revisit these equations. So I'm just going to take just a side divergent tangent here to redefine some new things. So the total mass of the galaxy is equal to the stellar mass plus the gas mass, which I could also say, just as well, say is the initial mass of the galaxy minus stuff that's ejected plus stuff that's accreted. So that's fairly simple. Okay. So I could equally well say this, dropping all the time dependence. Now if I take the derivative with respect to little s, I get 1 plus dg ds is equal to this stuff, the change in the ejected mass with respect to stars, the change in the accretive mass with respect to stars. And that allows me to simplify these two equations as follows. 1 plus dg ds is just equal to this thing, and we can see we have this thing kind of inherent in these two equations. So this equation can also be defined like this, and this equation can also be defined like this. So these are two equations that are going to be very important in the following slides. And we're going to make even further approximations, and we're going to say things, when we introduce the concept of a closed box model, we're going to be able to say there's no such thing as accreted matter, because it's a closed box. We're only going to start with the mass of gas that we have to start off the galaxy with. We're not going to be dealing with accreted mass anymore. We're not going to be dealing with ejected mass anymore. It's a closed box. So that you can see that these equations are going to simplify really, really drastically. If I get rid of this term here, then all we have is g d capital S ds is equal to p. It's going to be a very, very simple equation to solve. Okay, so the closed box model, we're going to posit that the mass in gas plus the mass in stars is m is equal to a constant. So if we're losing gas, it's because we're forming stars. If we're losing stars, it's because we're turning that stellar mass to the gas. We're going to assume that the metallicity is the metallicity of all of the galaxy as a function of time. So this metallicity dependence is only a function of time, not a function of space. So this is the one zone part of the model. The initial mass of the galaxy is entirely in gas. So g of 0 is equal to m, which implies that s of 0 is equal to 0. So this z, when I write this z equals z of t, I'm implying that it's not a function of space. Okay, so I went too fast. All right. So this is the tenets of the closed box model. Any questions there? All right. So now I'm going to combine the closed box model with the IRA. The IRA is not an individual retirement account. It is not the Irish Republican Army. It is, in fact, the instantaneous recycling approximation. So when we combine the closed box with the instantaneous recycling approximation, then we can say dg equals negative ds. That's just from the closed box model. If we lose gas, it's because we're forming stars. If we lose stars, it's because we're making more gas. So this is from slide 10. That's assuming the instantaneous recycling approximation. That's how the GCE equations have simplified when we assume the IRA. But now, with the closed box model, we can get rid of this term here, because in a closed box, we do not have any accreted material under the galaxy. So this thing just equals to p. And now I've gone from here to here by changing ds to dg. The only thing that happens there is we get a negative sign, just from the closed box approximation. And so now we can say, this is one of those things where all of the equations simplify, and we can figure out what the metallicity as a function of time is. The metallicity as a function of time is just equal to negative p, so negative the yield, times the integral from 0 to t of dg. So it's just negative p log g. That's what the metallicity of the galaxy is as a function of time. So the only thing it depends on is what is the effective yield of the stars and what is the gas mass of the galaxy. It's very basic. We can just figure out what the metallicity of the ISM is a function of time as long as we know what the gas mass is. So we can redefine this now as the metallicity of the galaxy equals p times the natural log of the total mass of the galaxy divided by the gas mass. And I'm going to define this thing as mu. This is the gas fraction of the galaxy. The g divided by m is just what fraction of the galaxy's mass is in gas. And so this is a very, very simple equation. The metallicity of the galaxy is just equal to the effective yield times the natural log of the inverse of the gas fraction. So all of these complicated equations have led up to this. So everything just simplified very beautifully when we assumed the closed box approximation and the instantaneous recycling approximation. Notice that nowhere in here do we care what the star formation rate was. When we assume these two approximations, we don't care if the stars were formed burstily, if the stars had a continuous star formation rate. It could have been some wild, crazy function that was like this. It doesn't matter. All we care about is what is the gas fraction of the galaxy right now. So the star formation rate could have been absolutely crazy.
The star formation rate was R, right? And
The star formation rate is psi. R is the return fraction. So
you're taking that to be constant because you took alpha to be constant in these equations.
correct.
What are you just looking at time scales in which that's not changing, or?
Just a moment.
I know that was a long time ago.
Don't worry, don't worry. Nope. We're going to figure this out. Sorry.
Oh, I should have said something earlier.
No, you didn't know. I was going to assume that we had a closed box. Okay. So here I'm assuming that alpha is not a function of time. That's correct.
Yes.
It's a function of the mass of the star. So as long as so the alpha is not a function of time because, let's go back to the definition of alpha. So you can see here alpha is just 1 minus r. R has nowhere in here does it depend on time.
Okay.
It's just the integral of whatever is returned from a certain mass of stars times an initial mass function. So if the initial mass function is changing with time, then we have a problem. But if the initial mass function is constant with time, then r is also constant with time, and therefore alpha is also constant with time. Is that good?
Yeah.
OK. I'm going to see if I can. Oh, I'm just going to. OK, we were here. OK. All right, so the current metallicity of the gas only depends on the gas fraction and whatever the effective yield is. We can also assume that the effective yield is constant. That's also not a very good assumption because the effective yield probably changes with the metallicity of the galaxy. But we're just going to assume for now that it's not a function of metallicity. OK, let's see what else we can figure out from this effective yield from this closed box IRA model. I'm going to define little z to be the metallicity of the gas divided by p, so it's just the metallicity of the gas in units of the effective yield of the galaxy. The average metallicity of the galaxy, the average metallicity in stars is going to be 1 over the stellar mass divided by the integral of the metallicity of stars from 0 to the total mass of stars. So this is just the definition of brackets, right? It's just the integral from 0 to s divided by total s. This is the average metallicity now of stars, not in the gas, but the average metallicity of stars. The average metallicity of the gas, that's not really a well-defined question because the gas is always well mixed. But once the stars are formed, they retain that metallicity forever. So the stars do have a spread in metallicity, and it's just whatever metallicity of the gas was at the time they were formed. And the way we figure out what the average metallicity of those stars is this equation. So this is just doing some integration. So we know that the metallicity is just the inverse of the gas fraction. And so the gas fraction is just G divided by M. So the inverse of that is M divided by G. And M is just S plus G, because that's what the closed box model says. We do some sort of substitutions here to actually perform this integral. And if you trust me, then it turns out to be this. You have to remember that the integral of log x is x log x minus x. I didn't remember that. And then what you get is the average metallicity of the stars is 1 plus mu log mu divided by 1 minus mu. And so if you know what the gas fraction is at a certain time in the galaxy, then you know what the average metallicity of stars is. And so that's a pretty neat result of the closed box model of chemical evolution. I'm just going to leave that up for a bit. Okay. All right, now let's see what else we can do with this closed box model. We know that the metallicity of the gas at any given time is negative natural log of G over M. Because remember, it was the log of M over G, so it's the negative log of G over M. We also know that G over M equals 1 minus S over M. That's just what the closed box model says. No, sorry, that's just performing this integral. So G over M is equal to 1 minus S over M, and that's equal to e to the negative z. Okay, so that's also a consequence of the closed box model. Now I'm just manipulating this algebraically. We know that S over M equals 1 minus E over Z. And so now we can play with these equations to get the metallicity distribution function, the MDF of these stars. Now this is one of those weird nomenclature things in astronomy. I do not know why they call it a metallicity distribution function. That seems redundant to me. Why isn't it just a metallicity distribution? I think it's so they could add the F in and make it MDF, which makes it less ambiguous than just calling it MD. But anyway, that's just a stupid linguistic thing that I never understood. Why is it a distribution function? Anyway. So Z ds dz, that's just what the distribution of stars looks like in metallicity. So now this is a slightly more detailed look at what the metallicity distribution of stars is. The previous slide we calculated what the average metallicity of stars is. This is what the metallicity distribution is. In other words, if we were to make a histogram of the number of stars in each bin of metallicity, this is the equation we would need. And so ds d log z is just proportional to z e to the negative z. So that's a consequence of the closed box model and the instantaneous recycling approximation. Again, no dependence on the star formation rate, and that's just because of the assumptions of the closed box model in the IRA. Now I'm going to have to open up VLC because the stupid movies don't play on this laptop. So just bear with me a moment. Okay, so what I'm going to pause this for a bit and explain what's happening here. So what I'm doing now is I'm plotting that equation, ds d log z, as I change the only free parameter in the equation. The only free parameter in the equation is the effective yield. So now I'm changing the effective yield in units of the solar metallicity. And as I dial up the effective yield, this is what happens. The peak of this metallicity distribution is going to get more and more metal rich. And in this particular equation, I've also figured out what the normalization of the equation is in addition to, so before we just calculated the proportionality constant, this movie also includes the normalization of the equation. So as I dial up the effective yield, you can see that the peak of the metallicity distribution gets larger and larger and larger. So it makes sense. If the stars are spitting out more and more metals, then the stars that are being formed later on should be more and more metal rich. So again, the only free parameter in this closed box model is what is the effective yield of the stars. And the effective yield is just what amount of metals are they making. And when I've labeled certain steps along this movie with the names of certain dwarf galaxies, I've given the effective yields of those dwarf galaxies. And so the original purpose of me making this movie was to explain the origin of the mass metallicity relation for galaxies, which is that as you dial up the effective yield, you make more stars, and the stars that you make are more metal rich. And so you can sort of get at some pretty basic stuff with galaxy evolution just by playing around with these galactic chemical evolution equations. This is sort of explaining the origin of the mass-metallicity relationship. Okay, back to this.
How do you get the plots for dwarfs?
So what I did there, the only thing I did was I just stopped froze frame.
Sure. So why do you choose to stop it at a certain point?
Do you remember the previous lecture where I had the metallicity distribution for Sculptor and I was fitting a chemical evolution model to it?
Yeah.
The result of that chemical evolution model gave me a few things, and one of them was the effective yield of those galaxies. And so these are the measured effective yields for these dwarf galaxies. And what I could do is also show you the observations of the metallicity distributions for those dwarf galaxies, and they'll roughly look just like this. So a closed box approximation is not that far off from the truth for some of these dwarf galaxies. It's actually pretty far off from the truth for Fornax, but it's not that far off for Sculptor and Ursa Minor. And we'll see later on in this lecture why it's far off for the truth from Fornax and what we can do to the chemical evolution equations to make it a better representation for Fornax.
So why does the yield depend on the galaxy? I thought this would be like something that's...
Excellent question. Excellent question. Excellent question. I will answer that briefly. Shortly. I'll answer it shortly. Okay. And hopefully briefly. Okay. All right. We already know this. We know this. We know this. Okay. Good. Okay. Okay. Remember, we also know the average metallicity of these stars is this. We already calculated that. This implies that the average metallicity of the stars is always less than or equal to the effective yield. So when the gas fraction goes to 0, the average metallicity of the stars approaches the effective yield of the system. So that's another consequence of this closed box model. And so if you can see here, if you let mu go to 0, then this term also goes to 0. Okay, and so here is, as I promised, the metallicity distribution for one of these dwarf galaxies, Canis Venatici 1. And here's the simple model. The simple model is just another name for the closed box model plus the instantaneous recycling approximation. And you can see it's a pretty good representation of what the observed metallicity distribution is. So some of these galaxies actually do look like closed boxes. Now, if you're very astute, you notice what I've plotted on the x-axis, which is iron. So who can tell me why it's a terrible idea to plot iron on the x-axis for this model? What does iron violate? Yeah. You're very correct, yes. So the iron is not instantaneously recycled at all. It's actually quite amazing that this thing does a pretty good job of reproducing the metallicity distribution when I plot versus iron. Now sometimes when I'm in a conversation about measuring iron abundance of stars, people always ask me, why do you measure iron? It's such a bad element to measure. Why don't you measure oxygen? Much I respond, give me a break. It's really difficult to measure oxygen in stars, and it's much easier to measure iron in stars. If I were to give you a plot of the metallicity distribution of oxygen in Canis Venatici 1, it would look like this, because there is no star in Canis Venatici 1 for which I can measure oxygen. I can, however, measure iron, and it looks pretty darn good for the simple model. And so that's telling you that for some reason, iron is sort of approximating the instantaneous recycling approximation in Canis Venatici 1. And the reason for that is the star formation rate is so slow in CanVen 1 that the delay time for iron is actually not that far off from the time scale for star formation in CanVen 1. Okay? All right. So now I'm going to relax one of the assumptions of the closed box model, which is that gas cannot escape the galaxy. So now I'm going to say gas can, in fact, escape the galaxy, but I'm still going to assume the instantaneous recycling approximation. This is called the leaky box. So gas doesn't come into the galaxy, but gas can get out of the galaxy. And in particular, I'm going to assume that gas escapes. No, sorry, I'm not assuming anything yet. I'm just taking this equation from one of the earlier slides, which is dGds is equal to the ejecta divided by alpha psi minus 1. And I'm going to define E over alpha psi to be eta. OK, now I'm going to assume that eta is a constant. So in other words, E is tracking psi. So the ejecta of gas is tracking the star formation rate. That's actually not a bad assumption, because the stuff that's blowing out the gas is supernova. And under the instantaneous recycling approximation, as soon as the stars form, they blow up as supernova. So if it makes a lot of sense, actually, to assume that the ejecta of gas follows the star formation rate, because it's just following the supernova rate. So the supernova rate follows the star formation rate. The ejecta rate follows the supernova rate. So assuming that E over alpha psi is constant is a pretty good approximation. So that's just assuming that the outflow tracks the star formation rate, which tracks the supernova rate. OK, so we know that G dz little s is equal to 1. We know that from slide 13. So now if we convert s to g using dg ds, then we know that this is equal to -1 over 1 plus eta. So now we know that the gas fraction at any given time is equal to e to the -1 plus eta over z. This should look familiar to you. This equation should look familiar to you. And the metallicity distribution of stars is looking like very much like it was with the closed box model. But now the effective yield we can redefine to be the effective yield over 1 plus eta. So, sorry, who was asking the question about? Yeah, OK. So you asked the question about how is the effective yield changing from galaxy to galaxy. So if we redefine the effective yield to now incorporate the outflow rate, then it's really not the stuff that's coming out of the stars that's changing from galaxy to galaxy. It's how much stuff is escaping the galaxy. So you can imagine that the potential wells of these galaxies might be different. So if the potential well for Ursa Minor, which was the lowest metallicity galaxy in that movie, is very shallow, then eta will be very high. It'll have a very high outflow rate. Whereas in Fornax, which is a larger dwarf galaxy, if it has a deeper potential well, then the eta will be smaller. And so the effective yield will be larger. Does that make sense? So in the leaky box approximation, it makes sense that the effective yield can change, and actually change quite a lot, can change by an order of magnitude. OK, so the functional form in the leaky box is exactly the same as the functional form in the closed box. The only thing that's changing is the coefficient in this exponent here. That does not change the shape of the distribution, it only changes the normalization of it. I mean, it pushes it to lower metallicity, but it doesn't change that overall shape, which looks kind of log normal, log linear. Now there's a problem here, which is called the GDorf problem. You've probably heard of this. Who has heard of the GDorf problem? OK, only one person has heard of the GDorf problem. All right, that's good. I can educate you by the GDorf problem. The GDorf problem, it's kind of an icky name for this thing. Basically, the metallicity distribution of stars in the solar neighborhood does not look at all like a closed box or a leaky box model. And it's called the GDorf problem because in order to measure the metallicity distribution in the 1970s or 1960s or whenever this was measured, they looked at GDorfs, which were long enough lived stars that they were sort of the integral of all of the past star formation. If we only look at high mass stars, then we're only looking at stars that formed very recently, and that would only be tracking the very recent metallicity history of the galaxy. But to track the long-lived metallicity history of the galaxy, we want to look back in time. So to look back in time, we need low-mass, long-lived stars. And so that would be G-dwarfs. This is what the metallicity distribution of G-dwarfs looks like. Now in oxygen, which is really appropriate for the instantaneous recycling approximation. So we can't say, oh, it doesn't match because it's iron. It's really oxygen, so it should be matching the instantaneous recycling approximation. It should look like a closed box if the galaxy is in fact a closed box. This is what the simple model predicts for the metallicity distribution in oxygen for G-dwarfs in the solar neighborhood. And this is what's observed. So these boxes are just the error bars for what's observed. And you can see that it's not a very good approximation for the observed metallicity distribution in the solar neighborhood. So one of the solutions to the GDorf problem is, of course, well, maybe the galaxy is not a closed box. Maybe it's not even a leaky box. Maybe it's an open box. Maybe there's some inflow coming onto the galactic disk as well. And so for the rest of the lecture, I'm going to see what happens if we also allow now for inflow to happen. And I'm sorry, I lost the clock on my computer. I'm just going to, actually no. What time is it? 12:20. OK, so I have 10 minutes left. All right, so the extreme inflow model is one of the models we're going to consider. We're going to consider two models. One's called the extreme inflow model, another one's called the best accretion model. So in the extreme inflow model, we're going to assume now not that G plus S is constant, but that G is constant. So in other words, as soon as we form a star, there's just the right amount of gas to fall into the galaxy to replenish the gas mass. So it's kind of a hokey assumption. And this is one of those times where we're going to make a hokey assumption just because we can get an analytical solution to the equations of galactic chemical evolution. The next best accretion model is even hokier. So we're just going to assume that G is constant. So every time we have ds dt, we're going to have an inflow of gas that it's appropriate to replenish G to keep it constant. Oops, I went a little too fast. We're also going to assume that the inflowing gas is metal-free. That's not a bad assumption. And we're going to assume that there's no outflow. So this is the exact opposite of the leaky box. It's the, I don't know what you would call that. It's like a water balloon that keeps blowing up. OK. So from slide 7, way 13 slides ago, we know that dg dt is equal to this thing. And we also know that the outflow rate here, F, because we know that E is 0, is equal to just to ds dt, and dgt is equals 0. So the outflow rate, sorry, the infall rate is just equal to the change in the stellar mass. And so that's equal to alpha psi. So from slide 9, we know that G d capital Z ds is equal to this thing. So how did we go from here to here? We divided by something. Oh, no, we know that ZF is 0, so this thing goes away. So that just leaves us with P minus ZF over alpha psi. F over alpha psi is just equal to ds dt. And so we can get this equation. And then finally, the metallicity as a function of stellar mass is just equal to this. And so in the end, if we just do all of the math, I'm just going to go a little bit more quickly now because I only have 10 minutes left. The limit as the stellar mass goes to infinity, because in this model, the gas mass is constant. And every time we form stars, the gas mass gets replenished. That means the stellar mass is just going to keep increasing. So now in this model, the limit of the metallicity as the stellar mass blows up to infinity is just the effective yield. This is sort of analogous to the closed box model, whereas as the gas mass went to 0, the metallicity approaches the effective yield. Here, as the stellar mass approaches infinity, the average metallicity approaches the effective yield. OK. This is kind of a hokey model. This one's even hokier. It's called the best accretion model. And now we're going to posit the same thing as before, that there's no loss of mass from the galaxy, that the inflowing metallicity is 0. And now we're also going to assume that the gas mass as a function of time is equal to this quadratic equation. And this is the simplest quadratic possible that satisfies having a maximum in G. So it reaches a maximum in G and then declines again. And also a smooth decay in G at late times as the star formation ebbs. So we know that typical star formation in galaxies tend to have a fall off, a smooth decay. And so this quadratic satisfies those two conditions, having a maximum and having a smooth decay. There's a free parameter here, which is m, and I do apologize on behalf of Bernard Pagel here for redefining m now. M is not the total mass of the galaxy. M is just called the accretion parameter. So this is just a new variable, which is not the mass of the galaxy. And I'm just adopting Pagel's nomenclature here, so I apologize. So if m equals 1, then G is just 1 minus S. That's the closed box. So the solution to this equation when m equals 1 is just the exact same thing as the closed box. So now we're going to solve this equation assuming that m can be arbitrary and some value greater than 1. So from slide 8, we know this. And then it turns out if you do a whole bunch of math, which I actually have never done, then the metallicity of the gases as a function of stellar mass is equal to this complicated thing, and the metallicity distribution is equal to this complicated thing. These two things are transcendental equations. You have to solve them simultaneously. But if you do that with a computer, I hope, then what you get is these family of solutions. So this is what the metallicity distributions of the stars looks like as you change m, from m equals 1 to m equals 20. What you get is a peakier and peakier distribution. So a closed box, you can see, is fatter than these best accretion models with m increasing and increasing and increasing. So what you get is sort of this low metallicity tail, but then this peak in the metallicity distributions of the stars at higher metallicities. So you can see that might be actually a pretty good thing to try for this GDorf problem. So let's go back to the GDorf problem, and you see that these two models here are actually variants of that best accretion model. And you can see they're doing a slightly better job of reproducing the metallicity function of GDorfs than this closed box model. So the fact is that introducing an accretion of gas into your chemical evolution model is a good thing to try when you're starting to see that you have a peakier, more metal-rich distribution than the closed box model predicts. And now I'm going to go back to VLC so we can show now the family of equations for the infall model. So now the free parameter that I'm dealing with now is the accretion parameter. As I dial up the accretion parameter, you can see this metallicity distribution gets peakier and peakier and peakier. And so if you have an observed metallicity distribution that looks like that, rather than looks like a closed box, then accretion of gas is a likely culprit for changing that non-closed box looking metallicity distribution into accretion looking metallicity distribution. Okay, with the 2 minutes I have left, I'm going to show you now the Fornax metallicity distribution. So the black histogram here is my observed metallicity distribution for Fornax in iron again, so remember it's violating the instantaneous recycling approximation. Here's what the closed box model looks like. That is the blue curve. The red curve is the same thing as the closed box model, but starting at a finite metallicity, so assuming that the initial metallicity of the galaxy is not 0. Still a bad fit to Fornax, but you can see that this best accretion model that we just went through is actually a pretty darn good fit to the shape of Fornax. And so whenever you see these narrow peaky distributions, still within the confines of the instantaneous recycling approximation, accretion onto the galaxy is a good thing to try. So numerical models are more sophisticated looks at solving the equations of galactic chemical evolution. So rather than dealing with these hokey analytical approximations and assuming all of these things just to find analytic solutions to the equations of GC, it's probably a better idea and probably simpler for your wrist for writing out all of these integrals. Just rather type them into your computer and have your computer solve them for you. That's exactly what I've done here for the Sculptor dwarf galaxy. And so because this is iron, what I can do in a computer that's much harder to do on paper is relax the instantaneous recycling approximation. I can incorporate the delay time distribution for these type 1a supernova that we saw in the previous lecture into the numerical models of chemical evolution, and thereby get a better approximation of what the metallicity as a function of time is. So this is still a one-zone model. There's no hydrodynamics in here. It's just this permeable membrane where we have gas flowing in, gas flowing out. But I can relax the instantaneous recycling approximation, and I can relax the closed box model part of these equations of galactic chemical evolution. OK, so that's it. That's the last slide of the lecture. Are there any questions?
So if there aren't any questions, I have a question.
Sure.
So, of course, as you well know, being at the institution you were sort of at and previously, or soon to be previously at, these dwarf systems are, of course, very important because they're perfect targets for indirect dark matter insertions.
Yep.
Both for WIMP annihilation and for light sterile neutrinos, for example.
Yep.
So, is there a unique So at issue with those dark matter insertions is the dark matter distribution and content. So for example, the content of dark matter in the field of view of some X-ray telescope, or the actual dark matter spatial distribution.
Yep.
So is it possible at all to connect that distribution and total amount of dark matter in these systems with some interesting nucleosynthetic tracer? At issue, of course, is these things come zipping through the disk, right? As they come through the disk, they're going to be tidally stripped of dark matter,
Yep.
And/or accrete dark matter, and these processes blow baryons out as we discussed, right?
Yep.
So, can you comment on that?
So I would say that, remember this leaky box model the only parameter is the effective yield, and the effective yield depends on the outflow of matter from the galaxy. So if the galaxy has a deep potential well, it should have a high effective yield. It should be hanging on to its stuff. So the best way I can think of to connect nucleosynthesis to how much mass content there is in these galaxies is what is the depth of the potential well. That should be dictated by the dark matter, not by the stars. So if the metallicity distribution is indicating that there is a very deep potential well, then that might be a better galaxy to look for dark matter in. That's
But what would be the signature of a deep potential well?
a high
These are all
effective yield.
relative, of course, but
Right, a high effective yield that you deduce from the metallicity distribution. That would be my guess. Now this gets a little bit screwed up because you have ram pressure stripping in these galaxies, so that can, you have ram pressure stripping of the gas, you have tidal stripping of the dark matter, so all of this chemical evolution happened before the galaxy fell into the potential of the Milky Way. And so all of this tidal stripping and ram pressure stripping kind of messes up the mass distribution a little bit.
are there any nucleosynthetic tracers of that? So you can see how many baryons got stripped out as opposed to being blown out by supernovas.
Yes, there is. Maybe I can pull up. I think this is it. Right. So I hate to toot my own horn here, but this is a paper I wrote last year where I introduced a new metallicity distribution based on ram pressure stripping. So basically, at a certain time, the galaxy was happily proceeding along according to a leaky box model. Let me zoom in on one of these things so you can actually see it. So here's Fornax, and you can see Fornax was happily proceeding along according to, sorry, let me show you a better one. Sculptor. So Sculptor was happily proceeding along according to one of its best accretion models, and you can see that this best accretion model doesn't do justice to the upper end of the metallicity distribution for Sculptor. So what I thought for Sculptor was maybe it fell into the galaxy, and this ram pressure stripping is a very fast process. I mean, it doesn't take very long as this thing swings around pericenter to get ripped out, to have all this gas ripped out of it. And so if that were to happen, then chemical evolution would cease very rapidly. So you would see this precipitous drop-off in the metallicity distribution. And so what I did was I started to alter the equations of chemical evolution to have the gas ripped out of the galaxy pretty violently at the end of chemical evolution to see if I could reproduce this wall in the metallicity distribution at high metallicity. And so there are some signatures for this very violent ram pressure stripping, which is having the metallicity distribution be truncated at high metallicity, even more so than this accretion model can reproduce.
I guess in terms of the instantaneous mixing, if we're treating it as a one-zone model, do you know what sort of timescale this is for supernova to ejecta to be mixed overall?
Oh, that's a very good question. So to mix through the entire galaxy would take a very long time, but to be mixed into the actual star-forming region, so there's, especially for the type 2 supernova, they're blowing up where stars are being formed. So I mean, you have these star formations that could last longer than the timescale of type 2 supernova, very likely last longer than the timescale of type 2 supernova. So by the time one fairly short burst of star formation finishes, it's already incorporating the ejecta of the first stars to blow up there. Now, in terms of the type 1A supernova to mix through the entire galaxy, that could take a very long time. So it's basically a hydrodynamical time for the galaxy, or a crossing time for the galaxy.
Oh, it was the same question.
Okay. Okay.
For the mass accretion model,
Yes.
is there a physical reason for them, or is it just a fit the data? Like, is there a physical reason you have some parameter m, or some reason to think that the accretion is this?
Is there some reason to think that gas is being accreted at all, or according to that rate?
According to that rate.
So no, those rates, that particular rate, that was the quadratic rate with the parameter m, that was strictly because that was the simplest quadratic that satisfied a maximum in gas mass and having a smooth decay and allowed an analytic solution to the equations. So like I said, it was kind of a hokey thing to assume. But in your numerical model, you could have a more realistic gas accretion rate. Oh, I should say that very happily, very coincidentally, that gas accretion rate actually tracks the infall of dark matter onto a subhalo for a low mass subhalo, according to Riese-Wechsler's 2001 paper. That's just a complete coincidence. And so if the gas accretion rate onto a small subhalo like a dwarf galaxy tracks the dark matter accretion rate, that's actually a pretty good assumption. That's just a major coincidence.
I'd be surprised at that, though. I mean, why would that be? I would imagine that you're going to tend to accrete dark matter down deep in the galaxy's potential well on some orbit.
Yeah.
That's where the ram pressure stripping is going to be most.
Oh, but this is for an isolated dwarf. If we're talking about an isolated dwarf galaxy. It's because this gas accretion. So let's go back to this. So this gas accretion rate that we're going to assume in the workshop today is T e to the negative t. And that is the same as this Wechsler et al. 2002 dark matter accretion rate. But this is for an isolated dwarf galaxy long before it ever hits the ram pressure stripping. Now, it's true that the gas accretion rate does not at all have to track the dark matter accretion rate, especially for massive spiral galaxies that have these cold flows and stuff like that. But for a kind of small dwarf galaxy, it may not be that far off.
Still, it seems like we're a ways, though, before you could tell me, like, with nucleosynthetic tracers and/or chemical evolution arguments, how much dark matter is in the field of view of my X-ray telescope.
Yeah, I totally agree with that.
Or whether we have a core or a cusp in dark matter and what that distribution might look like.
Yeah, I would totally agree. I would say that nucleosynthetic tracers are not the ones you want to deal with. It's rather kinematic tracers that you want to deal with. You don't like that.
Well, because the kinematic tracers aren't very good.
Well, yeah, that's true, but I would think that the nucleosynthetic tracers are even worse.
Is there prospect for them to be better?
I would say no. I would put my bet on the kinematic tracers becoming better before the nucleosynthetic tracers become better.
All right. Okay, well, thank you, Evan.